I would like to ask Guy Kushla to present us the paper titled Analysis of as Ncast 3.2% Si Slab to elucidate fundamental causes of the fracture mechanism clinking. Or clanking, I'm not sure.
Clinking.
Clinking.
You got it right first time.
Okay.
Great. Well, hi everybody, and good afternoon. My name is Guy Kushla, and I'm a PhD student at Imperial College London, looking at this process that happens in the primary processing of steels called clinking. And I'm also working with Dr. Katrin Davies, who's over there, and with Tata Steel as well, as the industrial sponsor for this PhD. So, what I'm going to talk to you about today, I'll run you through, is a bit of a background to clinking, because I'm sure most of you don't know what clinking is. A little bit of what the problem is, then a bit of our current thought process about the kind of fracture initiation mechanism going on called transverse cracking, and about our kind of current approach, which is part of a wider PhD, so this is kind of a small segment of it. And we're going to take you through the approach of our testing. We're going to take a look at some Charpy test result data to take a look at the brittle to ductile transition of this as-cast material. We're going to take a look at the microstructure of the as-cast material. Then we're going to take a look at basically how elements can segregate throughout that microstructure using a type of testing called X-ray fluorescence, and also do some EDX analysis, which looks at the points, the composition of various different points in the as-cast microstructure. Then we'll draw some conclusions. Okay, first of all, a bit of a background to the problem. This is a schematic, a very rough schematic of what primary processing of what a steel plant looks like. So you have a division called concast, which is where you cast the steel, taking it from a liquid into a solid. A lot of steel plants now have this thing called continuous casting, so you pour in molten metal in, and it kind of goes from vertical 90 degrees and bends around to going flat, and you come out with these big slabs of steel. So you're going from molten metal to, as it comes out of concast, around 800 degrees Celsius. Then it goes, for a lot of steel plants, it goes from concast to this division called hot mill. And the hot mill, what you're doing is you're taking it from a big slab of steel and rolling it into very, very, very thin sheets. When it goes into the hot mill, the first place it goes through is the furnace, where it gets reheated back up again. So it comes out the caster quite hot, gets cooled down a little bit, and then goes into the furnace to be heated up again and then rolled into shape. However, there is this gap in the schematic, which I purposefully put in, which is in a lot of steel plants, there is this time gap where you have to almost transport your slabs of steel from your continuous casting division to your hot mill. And during this time, and there are a number of times this process can happen, you can either get this fracture process called clinking, when it's cooling down after continuous casting, and as it's cooling down, the whole slab just fractures and breaks apart. So you get a full catastrophic failure, not just like a small crack, but a full catastrophic crack. Or when these slabs, which might not have catastrophically failed like this, go into the reheat furnace, they can then break apart. Now, if they break apart in what the reheat furnace is, that is a really, really catastrophic problem, because it takes about a week for the slab to cool down. It's really hard to get that slab out of there. So you really want to avoid the thing on the right. The thing on the left is a bit of a shame, but you're not that worried about it. Now, the thing that we know from this is the fact that actually when it cools down to a very low temperature, this happens much more frequently. So, a little bit of an overview. Bear those two pictures in mind. Things that we can understand about clinking so far are the fact that the cracks are transverse, so they are running perpendicular to the direction of casting. So if you imagine you're casting a slab in that direction, all the cracks that we see are running perpendicular to that. We know that it's quite a loud and fast cracking, so through that we get kind of thinking this is a brittle fracture mechanism. The large catastrophic failure is brittle, and that's the reason why it got kind of denoted the name clinking, is because it kind of makes a clinking sound whenever it breaks. And it occurs much more frequently when it's left to cool down, for an extensive period of time. So if it goes straight from the caster into the reheat furnaces, then normally it's kind of okay. Whereas if it's left to cool down for a really long time, it will either break apart as it's cooling down, or when you put it into the reheat furnace, it's much more likely to break apart. So something's very temperature dependent about this process. Currently, what Tata Steel do, and I'm sure a lot of other steel industries do, is something called hot charging. And what hot charging is that when it comes out the continuous caster, instead of just chucking it onto a slab yard and letting it cool down, you put it into a really warm insulated box and make sure that temperature stays quite hot. And they have seen that this massively reduces the extent of clinking, or the frequency of clinking that happens. They also can know that it's a function of the composition. So the frequency of this happening happens loads in some alloys and not very much or not at all in other alloys. So something compositionally is changing between each slab of steel. So we've taken an image of what a fracture surface kind of typically looks like for a clink crack. And what we kind of noted is that actually where we think the point of initiation is quite close to the surface of the slab. This has kind of been noted through various different ways that people tend to think that this fracture point is quite near the surface of the slab. Again, we can't be 100% sure about this because this is mostly based on kind of conversations you have, but this is kind of the one picture that we have where we really think this is it, because you've got quite a flat fracture point there. So just slightly subsurface. It tends to occur also from all the images that we've seen, occurs in the center and then propagates outwards. And that kind of smiler, this crack is called the smiler crack because obviously it looks very smiley, but that is what we think is a band of rust forming where the crack's propagated and then rusted on the bottom surfaces. What we also see when slabs are left in the slab yard to cool down for quite an extensive period of time, what you also see is that actually you might not get the whole slab breaking apart and snapping in half like the top image, but you actually see quite large cracks that form just through the thickness but haven't necessarily broken the whole slab apart. And what's interesting about these as well is that these often occur at regular intervals along the slab length. So you've got one there, and then, you know, 1.5 meters later you've got the same thing, 1.5 meters later you've got the same thing. So what I'm going to talk about now is possibly our thinking about how these cracks start. So this diagram here on the bottom, this is kind of a typical diagram of a lot of casting defects that you might have. So it's well known within the casting industry that you can form just a lot of defects. The ones that we're particularly interested for the nature of this problem are these deep oscillation marks, which are kind of dents in the surface, which form when it's being continuously cast, and also transverse cracks. The reason why we're interested in these is because we know that transverse cracking, as I'll explain in a little bit of time, is a function of the composition, but also as well, these defects are in the same orientation that we see the cracks happen. So, the other thing that we've determined through some various finite element modeling in a different part of the PhD is that you, and a lot of other researchers have understood this, is that you get quite large longitude, when you cast something, you get very large longitudinal stresses. So in the direction of your casting, you're actually getting very, very big stresses. The sources of these big residual stresses can be from a number of things. Most kind of pertinently is the non-uniform cooling. When you're casting a big slab, it's really quite thick. So obviously, it's not all going to be at the same temperature. You're going to get big temperature differences in it, and those are going to cause stresses. On top of that, you've also got transformation stresses, which is dependent on your composition. You've also got mechanical stresses as you're bending the slab of steel as it's going across various different rollers. And also as well, the process route through the plant is actually quite intrinsically important. If you start throwing slabs of steel around, or if the tractor drops it, then that can actually cause a lot of input of stresses as well. So that kind of diagram there, that picture there, hopefully explains kind of what our thinking is. These big stresses here are pulling that crack apart, and you're getting a mode 1 failure. This is from a Russian paper which we looked at ages ago, which actually kind of is backing up our thinking and our modeling, saying that actually over the course of you cooling, and that's looking at their models of the stresses over time, you're actually increasing the amount of residual longitudinal stress. So you can see right at the bottom there, after it's been cooling for a really long time, the units there, I know it's very difficult to see, but that's actually about 600 megapascals. That's from a slightly different type of casting, but kind of backs up our thinking about what's actually going on. And our thought process today, or our kind of our idea, which you can agree or disagree with, is that these transverse cracks are acting as our site initiator to then instigate that catastrophic failure. And these cracks are propagated by longitudinal stresses. So let's dive a little bit deeper into what transverse cracking actually is. Oh, I'm running out of time. Okay, transverse cracking occurs this thing called ductility troughs. So when you're going from a high temperature to a low temperature, so you're cooling down, what you actually see is you see these at kind of particular temperatures, you see this massive drop in ductility. And that drop in ductility is due to composition. It can occur, depending on the alloy, between about 600 and 1200 degrees Celsius. Massively depends on composition. These three microalloying elements are known to be quite detrimental for various reasons, which we'll go into a bit. They pin the matrix, reducing the strain to fracture, and they also delay recrystallization, helping recover ductility. Now this transverse cracking occurs due to this massive drop in ductility during the unbending and straightening operation, which is there, as it kind of turns 90 degrees. You put in these strains, and when that happens on the ductility trough, you get fracture. So how does this actually happen? If you're really hot, you have purely austenitic grains. Then as you start to cool down, you get a phase transformation. You get ferrite forming typically on the grain boundaries first. And you get this kind of film-like ferrite, which is called deformation-induced ferrite. This happens on prior austenitic grain boundaries. The ferrite is softer than the austenite at these high temperatures. So then when you put, then you get voids, second phase particles, and then when you put in a small strain associated with that unstraightening operation, you get voids forming around these, you get the strain concentrated, in the ferrite phase, and voids forming around these particles. So our approach to testing, we've got this as-cast slab. We're looking at 3 different locations from top to bottom. We're going to do EDX, which is looking at the composition of particles, specifically around the grain boundaries where we think this fraction might happen. We're looking at XRF, which is looking at the bulk composition through the thickness of the slab. And we're also going to take a look at Charpy tests as well. And we're looking at these through the location of the slab, so analysing where that ductile to brittle transition might be. And we're then going to also look at the optical microscopy, looking at the grain structure and what that's like through the thickness of the as-cast slab. So, first of all, our kind of Charpy results. We noted that actually through the thickness of the slab, we're actually getting the same Charpy results, the same ductile to brittle transition temperature, regardless of the location through the slab. You're getting a very high ductile to brittle transition temperature, somewhere around 220 degrees. This is great news because it means that actually what these steel plants are doing by keeping them really hot and not letting them cool down is making sure that they're actually staying very, very ductile, and if they let them cool down, you're entering into a very, very brittle range, when the slabs get below 150 degrees Celsius. Looking at optical microscopy, I've just taken some samples there right at the surface, number 1, number 2, number 3, and you can see them there. I'm not sure how good the definition is for you guys, but what you see in these as-cast samples is massive, massive columnar grains. They're slightly smaller the closer you are to the surface, where you tend to get a chill zone, so you get equiax grains, but then the deeper that you go into the sample 2 and 3, they're really big. The scale bar, I'm sorry that you can't see, but if you take a look at that scale bar, that's actually 2 millimeters. So the size of these squares are about 10 millimeters each, so if you kind of think about the size of those grains, they're pretty large. You're also getting dispersed perlite. Is what we kind of think of as the microstructure. Looking at the change in composition through the thickness of the structure, we took a look at 3 locations here, kind of 1 midway subsurface, 2 and 3 being kind of right on the surface. Taking a look at the composition of this high silicon steel, so these are normalized compositions, so just normalized with what the actual composition is. The ones that are particularly interesting are actually aluminium, which we know forms quite detrimental aluminium nitrides, which are where the second phase particles that voids can form around, especially during transverse cracking. And we can see that actually in certain locations, for example at 20 millimeters, location 1, you've got no aluminium shown at all, but in other locations you've got quite a lot of aluminium. So that might be important, and something that we need to look into a lot more to see actually how, even though you might think your composition's A-OK, you, as a whole macro surf, as a whole kind of on the macro level, but actually within the slab you can get segregation where elements of bad particles can segregate to bad locations. Don't worry, I'm very close to finishing. Manganese, another bad one that can form manganese sulfides, also uniform through the thickness. And then the highlight is EDX testing, where we're looking at kind of point compositions. And so we've taken one, sorry I don't have the scale bars for this, but that one, if you imagine the scale bar there is at about 200 micrometers. We've got spectrum 1, spectrum 2, looking at probably those cementite regions, then spectrum 3 and spectrum 4 there. So you can kind of see that line across there, that's looking at a grain boundary. And then there's a big second phase particle there, spectrum 3. When we look at those compositions for those various different spectrums, what's really interesting is actually this spectrum 3, where essentially looking at that kind of composition, we've really got a manganese sulfide particle. And if you can look closely around that spectrum 3, what we're also seeing is some void growth around that particle. So that, I think, is backing up our kind of thinking here, that actually what you tend to get, and this sample that we've looked at here is at a room temperature as-cast microstructure. So even though this slab itself hasn't fractured apart, you can see that we're probably getting some void growth around these quite big second phase particles on the grain boundary. The spectrum 1, spectrum 2, and spectrum 4, the actual particles on the grain boundary, spectrum 4 is probably cementite, looking at that composition. So, this is a very initial study into looking at the microstructure of an ASCAR slab, and there's much more work that we kind of plan on doing to kind of validate our current thinking and to look into stuff a little bit more. But our Charpy testing shows that we've got a very high transition temperature, around 210 degrees. This validates the use of hot charging. Great news. We're getting some really large second phase particles, especially in and around the grain boundary region, thinking that these are actually acting as initiation sites for transverse cracking. Remember that transverse cracking is a very small cracking, and that transverse cracking is then acting as initiation floor for the big catastrophic clinking. XRF is showing some distribution of some of the detrimental elements, such as aluminium, but you're getting a homogeneous distribution of manganese and sulfur. We want to look into this a little bit more, doing EPMA, which is those elemental maps, so seeing actually how elements segregate throughout the entire slab. That's our big plan. Another element which I haven't shown in this presentation, but is really important for this kind of phenomenon, is that you saw that we're getting very, very large columnar grains in our microstructure. In a few other studies, they've kind of shown that actually those columnar grains, and through some EBSD work that we have done, that actually those grains are forming on the very weak 100, which is the preferential plane for cleavage fracture. And so that is a certain element of our testing going forward that we're really going to be analysing and looking at how susceptible ASCAR slabs are to clinking. And that concludes the presentation. Thank you very much for listening.
Thank you very much.